password to launch the nuclear weapon, and the password was shared among top three entities of the country, namely the president, the prime minister, and the defense minister. And the password was shared among these three entities in such a way that only if at least two of the entities come together, then and enter their respective shares of the password, the missile can be launched. But if only one of these three entities.
Sorry to interrupt. If you are sharing the
Yeah.
screen, we are not able to see it. So we just see the opening screen from you.
But I have shared the file. It's not showing to you?
Yes. Could you reshare it again, sir?
Okay.
So actually there is a share icon, share content icon.
Yeah. So it
Yes.
So when I share this PPT, it is opening it, and now it is showing me loading file.
Actually, we are just seeing the opening screen of yours. It says tutorial for Connect 2020.
Now?
Now as well. Yeah. You're not able to see the transitions of the slides.
But I am able to see the transition. Why this is happening?
One second. I think you are okay. Could you reshare it again? Yeah, perfect. So we are seeing the motivation slide right now.
Yeah. So you have seen the motivation slide. Now can you see?
Now it is secret sharing motivation.
Yeah. Okay. So
all set, sir. Good to go. Yeah. Please carry on.
Yeah. So as I said, I gave you two examples. So in example one, the scenario was that the password for the bank locker should be secret shared among the three managers in such a way that only if two managers come together and enter their respective passwords, the locker should open. But if only one of the managers enter her password or his password, the locker should not open. Right? And in the second application, the problem was that you have the password to launch the nuclear missile, and it is secret shared among three entities of the country in such a way that only if two entities enter their respective passwords, the missile can be launched. Otherwise, the missile cannot be launched. Okay. So there are plenty of such scenarios where I would like to share my data among multiple entities in such a way that only if certain fraction of those entities come together, they can get access to the data. But if sufficient number of entities do not come together with their shares, then the data should not be accessible. So this, the previous two examples can be abstracted by this general problem of N, T secret sharing, which was introduced long time back in 1979. The problem is as follows. So you have a set of parties. So I assume there are N parties, which I denote by P1 to Pn. And you have a special entity among these parties called a dealer. So you have a dealer D at the top who has some secret value, secret data S. It could be a bit, it could be a password, it could be a long file. So I abstract it and say that he has a secret input S from a secret space or the set of all possible secrets, which I denote by this calligraphic set S. So he has a secret value and he wants to share that secret S among N entities. So those N entities are P1 to Pn by giving each entity a piece of that secret S. Okay. So that piece of information about the secret S which is given to the respective parties is called the share. So the shares I am denoting as S1 to Sn. The first share should go to the first shareholder, the second share should go to the second shareholder, and the nth share should go to the nth shareholder. So the distribution of the shares should be done in such a way that following two properties should be satisfied. The first property is that if any T shareholders among these N shareholders come together and exchange their shares, they should fail to access the secret S. That means whichever set of T parties. It could be the first set of T parties, it could be the last set of T parties, or any set of T parties. If they combine their shares, by combine I do not mean concatenating. By combine means you apply some algorithm and try to recover back the secret. So the property I want here is that if you have only T shareholders and they combine their shares, the secret should not be reconstructed back. But if T plus one or more shareholders come together, then they should be able to get back the secret S. So T is acting as a threshold here. So N and T will be parameters for you, and you can control the parameter T. So depending upon the value of T, uh, you get N comma T secret sharing. So if I take the missile launching application and the locker application, there my T was 1. I need at least 2 participants to come together to get access to the password of the locker or password for the launching of the missile. But if only T equal to 1 participant come, then the secret or the data should not be accessible. Okay, so let's see a very simple example or simple construction of a secret sharing where my threshold is n minus 1. That means I need a mechanism to distribute my secret among n participants in such a way that until and unless all the n shareholders come together, they should not be able to get back the secret, right? So it's like saying if n is equal to say 100, and if you have distributed your secret among 100 participants, the distribution should be done in such a way that even if 99 people come together with their shares, they should fail to find out what exactly was the secret which is shared. Only when all the 100 participants come together, they should be able to get back the secret. So the scheme is very simple. And here I am assuming that the secret which dealer wants to share is an L bit string. So that's why the secret space here is the set of all possible L bit strings. Your L could be anything. L could be 1, 2, it could be 1 GB, anything. So you imagine that the dealer has an L bit secret value which he wants to secret share. So to do that, what the dealer does, it does the following. The first n minus 1 shares it randomly picks. So this notation belongs to and subscript R denotes that these values are randomly chosen from the set of L bit values. So the first n minus 1 shares are random random strings of length L bits. So these will be the shares for the first n minus 1 participant. And once the shares for the first n minus 1 participants are picked, the share for the last participant is decided as follows. It is said to be the XOR of the first n minus 1 shares and the secret is. Okay, so I hope all of you understand what's the XOR operation. XOR of the two same bits will give you the value 0. If XOR of two different bits will give you the value 1. So it's like saying addition modulo 2. Okay, and once the shares S1 to Sn are computed, they are given to the respective shareholders. So S1 will be given to the first shareholder, S2 will be given to the second shareholder, S of n minus 1 will be given to the n minus 1 shareholder, and Sn will be given to the last shareholder. Now let's see whether this simple distribution of the secret S satisfies my requirement or not. So the first requirement was that if all the n shareholders come together, they should be able to get back the secret. And this is very easy to check, because if indeed all the n participants come together, we will have all the n shares S1 to Sn available. And if we combine them by just XORing these n shares, we will get back the secret S. Because if you see, the relation between the secret S and the n shares was that if you XOR the n shares, you will get back the secret S. And indeed, if all the n shareholders come together, you will have all the n shares, and you can XOR them and get back the secret S. Now let's understand the privacy property. The privacy requirement was here that if any set of n minus 1 shareholders come together, they should not learn what is the secret is. That means even if one share is missing, the secret is not reconstructible. And the proof can be divided into two cases depending upon which set of n minus 1 shareholders you are considering. Case 1 could be when the n-1 shareholders which you are considering are the first n-1 shareholders. So if I consider the first n-1 shareholders and imagine that they are bad, that means they are colluding and they are trying to recover back the secret, then it is easy to see that they will fail to find out what exactly is the secret is. Because the first n-1 shares, they are picked independently of the secret is. If you see the way shares have been computed by the dealer. That means the first n-1 shares, they have absolutely no relationship with the secret is. That means the secret could be any value. It doesn't matter what exactly is the value of the secret is. The shares of the first n-1 shares are completely unrelated to that secret. The second case could be when the n-1 shareholders, which I am considering, which are the bad ones, include the nth shareholder. And in that case, it might look like that since the nth shareholder is also under the control of the bad guy or is colluding and trying to recover back the secret, something might be learned about the secret S because the last share is dependent on S. That's the way the last share was computed by the dealer. But that's not true because even though the last share S of n was dependent on the secret S, it was also dependent on n-1 shares, the first n-1 shares. Now I am assuming here that only n-1 shareholders are colluding, including the last shareholder. So if that's the case, that means at least one of the shareholders among the first n-1 shareholders is not in the collusion. And the share for that particular shareholder was randomly chosen and independent of the secret S. So even if the collusion of n-1 shareholders include the last shareholder, it still holds that those n-1 shares are completely independent of the actual secret S. So that shows that this simple scheme of dividing the secret as the XOR of n values and those n values being the same size as the size of secret satisfies the requirement of an n, n-1 secret sharing. But in general, I might be interested to construct a secret sharing scheme for any threshold t. So the previous construction was for threshold being t equal to n-1, right? But in general, my threshold t could be any value. It could be n over 2, it could be n over 3, it could be n-2, and so on. So a general question is that how do I design n comma t secret sharing where t is not exactly n-1 but rather a value less than n-1. Okay. So what we can do is we can get a solution for a general value of t as follows. We have the set of n participants. We divide the set of those n participants into various groups of t plus 1 size. Okay. So there will be multiple such subsets. So I divide the set of n participants into subsets of size t plus 1. And for each such subset of size t plus 1, I run an instance of additive secret sharing, assuming that the secret need to be shared only among that subset of t plus 1 parties. Okay. So what I am saying here is demonstrated by this example. Again, I am unable to run the animation here. This is an online WebEx meeting. This would have been demonstrated to the animation here, proper animation, and that's why everything is kind of rendered here, appearing together simultaneously. Sorry about that. So here the example is n is equal to 4. So you have 4 shareholders and you want to design a secret sharing with threshold t equal to 2. That means you want to distribute the secret among those 4 shareholders in such a way that if any subset of 3 shareholders come together, they should be able to get back the secret. But if only 2 shareholders pull together their shares, they should not be able to get the secret. So as I said here, what I'm going to do is I'm going to divide the 4 participants. The 4 participants are P1, I'm going to divide those 4 participants into various groups of 3
Sir, we are not able to hear you.
Okay. So
yeah, this is better.
Yeah, can you hear me now? Okay,
Yes.
fine. So what I'm doing now here is I'm dividing the set of 4 participants into groups of size 3. So the first group has 3 participants, P1, P2, P3. The second group has participants P1, P2, P4. And the third group has the participants as P1, P3, P4. And the last group has the participants P2, P3, P4. Okay, and these are the all possible subsets of 3 participants that I can form out of these 4 participants. Now for the first group where my participants are P1, P2, P3, I run an instance of secret sharing, assuming that the secret needs to be shared only among these 3 participants. That means I am ignoring the 4th participant here. I am assuming that he is not in the list, not in the contention. So how I'm going to distribute the secret among these 3 participants? Well, I run an instance of additive secret sharing by picking random shares S11, S12, S13 such that the XOR of S11, S12, S13 is the secret S, and I distribute S11, S12, S13 to these 3 shareholders respectively. Now for the second group, my participants are P1, P2, P4, and I assume that P3 is not in my list, and I pick 3 shares for the same secret S such that these shares sum up to the secret S, and I distribute the 3 shares to the participants P1, P2, P4. Same thing I do for the third group by picking another set of 3 independent shares, and same thing I do for the fourth group by picking another group of 3 independent shares. Okay. Now why this is going to satisfy your privacy property? If you consider here, we want that if only 2 shareholders come together or only 2 bad guys collude, they should fail to get back the secret S. Now, if I consider P1 and P2 to be the bad guy, then it doesn't matter in which group they are. They might be in the first group, they might be in the second group, they might be present in the third group, they might be present in the fourth group. They will always miss 1 share because they will be part of a group where there is always another guy with those 2 guys. And that group, the secret is secret shared with threshold being T. So that's a simple intuition because of which this secret sharing scheme satisfies the requirement. And if I consider any set of T plus 1 shareholders, they will be able to get back the secret because there will be at least one group where those T plus 1 shareholders will be the only participants where the secret has been shared, and the shares with respect to that group will be sufficient to recover back the secret. So even though this is a very simple solution, the downside of this approach is that the number of subsets that I have to consider becomes very large if my threshold becomes say n over 2, right? So if you have say 100 participants and if you have t is equal to 50, then you have to consider 100 choose 50 number of subsets, and for each such subset you have to run an instance of secret sharing. So the number of subsets become exponentially large as the value of n and t increases, and t is roughly half the participant size. So that's why this solution will become impractical for large values of n and t, and that's why we now need a solution which should be practical and very easy to implement for any value of n and t. It doesn't matter what's the value of n and what's the value of t. So this secret sharing scheme is called as Shamir's secret sharing scheme. It's just a 2-page paper, a very simple solution, but this solution has a tremendous impact. It is one of the most widely cited cryptographic algorithms. So the idea behind the Shamir's secret sharing is as follows. So if you have the secret S, then the idea here is that to share it, you pick a random polynomial in 2 dimensions. I call that polynomial as f of x, and the degree of the polynomial should be t, namely the threshold t. And the polynomial should be a random polynomial with the only exception that its constant term should be the secret which you want to share. Okay. So for instance, if t is equal to 1, what I am saying is that to share the secret S, you pick a straight line, say this black straight line. Okay. It's a randomly chosen straight line from the xy plane with the only condition that its constant value is the secret S. Okay, namely the value at x equal to 0 should be S. And you can see there could be infinite number of lines possible. It's not just that this is the only line which passes through y equal to which passes through this secret S. There could be multiple straight lines whose constant value can be secret S. In fact, there are infinite number of straight lines which can pass through this point S. Okay. So now once you have selected the straight line which you want to use for secret sharing, the shares are computed by just evaluating that straight line or evaluating that polynomial at t plus 1 distinct values. So again, if I take t equal to 1, the shares are evaluated or computed by picking distinct points on that straight line, except the value at x equal to 0. And so for instance, if I pick the straight line and evaluate it at x equal to alpha 1, x equal to alpha 2, and x equal to alpha 3, where alpha 1, alpha 2, alpha 3 are publicly known, then they can be considered as the shares for the secret S. Okay. So why this is a valid secret sharing? So it's based on two facts. The first fact is that if I give you any set of t plus 1 distinct values on a t degree polynomial, then you can uniquely get back that polynomial which was used to do the secret sharing. So for instance, if I don't tell you the straight line which I have used for doing the secret sharing, but if I give you two shares, those two shares could be S1 or S2 or S2 S3 or S1 S3, then those two shares are nothing but 2 points on an unknown straight line. And 2 points on an unknown straight line are sufficient to recover back the original straight line. But if I give you only one share of the unknown polynomial or unknown straight line, then you can't pinpoint what exactly was the straight line which was used. So for instance, if I give you the share S1 and I challenge you, can you tell me what was the secret S which is used? So that S1 is the share for that secret, you can't pinpoint because through this S1 there are infinite number of straight lines which could pass. So it could be this blue line which could pass through this S1, and if that's the case, then S double prime could be the secret, or it could be this red line which could pass through this S1, and in that case S prime could be the secret, and so on. It's only when I give you 2 or more points or 2 or more shares you will be able to find out what exactly is the secret which dealer has shared. That's a simple observation, right? And that's all. That's a simple secret sharing. So I am skipping the formal details here. To implement secret sharing scheme, what we have to do is we have to pick a finite field. We can't pick the polynomial over the real numbers or over the integers because there are certain issues with respect to the security, and that's why we perform all the computations and operations over some finite field. On a very high level, finite field is a set, and it will have two operations, a plus operation and a dot operation, which more or less satisfies almost all your properties that the regular integer addition and the regular integer multiplication will satisfy. So assuming we are doing all our arithmetic over finite field, the secret sharing scheme of Shamir is as follows. If you are the dealer and you have to share a secret S, you pick a random polynomial f of x. Okay, so it's the dealer who is picking the polynomial. The participants will not be aware what exactly is the polynomial chosen by the dealer. So the polynomial will be randomly chosen, namely its coefficients a1, a2, at will be all randomly chosen from the finite field, but the secret should be, but the constant term should be the secret which dealer wants to share. Now once the polynomial is chosen, the share for the ith party is nothing but the value of that polynomial at xi, where x1 to xn are publicly known. So the first shareholder will get the value of that unknown polynomial picked by the dealer at x equal to x1. The second shareholder will get the value of that unknown polynomial at x equal to x2 and so on. So that's the idea of Shamir's secret sharing. And it's very easy to implement Shamir's secret sharing. Okay. So now let me go to the second problem which I wanted to address or touch upon in this tutorial. This problem is about secure multi-party computation, which is a very fundamental problem in secure distributed computing. So the problem here is as follows. You have a set of n participants They might be present in different parts of the globe. They are connected, of course, by channels. Over the internet, they are connected. And the parties, they do not trust each other. Okay, they might be competitors. Okay, and so on. So each participant has here some private input xi. That xi could be a bit, it could be a file, it could be a database, and so on. It depends upon your underlying application. And there is some common function f, right? And that function f is an n-array function, namely it takes the inputs of all the participants. Now the goal here is to design a protocol according to which these participants should talk to each other, should communicate messages with each other, so that at the end of the protocol, the participants learn the value of the function on the inputs of the n participants. But this should be done in such a way that each participant should not learn anything beyond his own input and the function output. So for instance, participant P1 should not learn anything beyond his own input x1 and the function output. That means the privacy of the inputs of other participants should be preserved. Right? That's why I'm calling it secure multi-party computation. Multi-party computation because multiple parties are here who are collaborating to do some computation, and secure because you want to preserve the privacy of the respective inputs. Why this is a very important problem? Because there are plenty of applications in the real world which can be modeled by this abstract problem of secure multi-party computation. Let me give you a very simple example. Everyone now these days is interested to do machine learning. And machine learning, the accuracy of the machine learning applications depends upon the diversity and the volume of data on which you are running the ML applications. So if the data is coming from various entities and multiple entities and it has huge amount of variance, then you will expect that the accuracy of your ML algorithms will be better. But it turns out that this data is not going to belong to a single entity. So imagine a scenario where you have big tech giants, say Google, Microsoft, Amazon, IBM, Yahoo, each of which has its own enormous amount of data. And now together they would like to collaborate and run a machine learning application on the combined data spread across all the tech giants, right? But here the tech giants, they are competitors. They may not be willing to reveal their individual data, individual values to each other, because that's what is their revenue, their business, right? So what we require here is a solution where these tech giants, without worrying about the privacy of their data, are able to collaborate in such a way that the ML application is run on the combined data, but the privacy of the individual data is preserved. So how exactly this can be done? So you can see that this follows under the problem of your framework of secure multi-party computation. You have multiple entities, each of them has their own data, and the function which they want to compute is the machine learning function. So how secret sharing can be useful here? So what we can do is we can imagine that, say, these tech giants outsource whatever function they want to compute to a set of three servers. These three servers can belong to three different service provider and so on. And they do not give the data in clear to these three servers. Okay, so each of these tech giants secret share their data among these three servers. So if you take Google, whatever data it has, Google acts as a dealer and it secret shares its data among these three servers. Microsoft takes its data, act as a dealer, and it secret shares its data among these three servers and so on. And if I assume that among these three servers, these three cloud service providers, majority are honest, majority are good ones. Say two of them are good and only one is bad. And if the threshold of secret sharing is set to t equal to 1, then even if one of the cloud service provider gets corrupt and collude with any of these tech giants, the privacy of the individual data is preserved because the individual data is secret shared with threshold being t equal to 1. So that takes care of the privacy of the data. So each tech giant has secret shared their individual data among these three cloud service providers. Now, whatever ML application was supposed to be performed on the clear data will now be performed on the shares of the data. And that will be the essence of a secure multi-party computation protocol, right? So on a very high level, the computation on the shares is performed as follows. This is a fundamental fact that any computation can be expressed as a sequence of addition and multiplication, right? So you write any program, any function, any C function, all the operations that you can use in that function can be finally boiled down to a sequence of addition and multiplication. So once the data has been secret shared among these three cloud service provider, whatever is the sequence of addition and multiplication that needs to be performed on the clear data will now be performed on the shares of the data. And when we will be performing the sequence of addition and multiplication on the shares of the data, at no point of time the backend, namely the current server among these three service providers, will learn anything about what exactly is the content of that share, what exactly that share corresponds to. So the idea here is that instead of performing the computation on the clear data, you now perform the computation on the shares of the data, and that sharing has a property that any one share is independent of what exactly is the data, but two shares will be sufficient to recover back the data. So once the entire computation has been performed on the shares of the data, and you have the output of the ML application, ML algorithm in a shared fashion, right? Then you can reconstruct back that output by just exchanging the shares of the function output. So starting from the input to output, everything remains available in secret shared fashion, but no intermediate value is revealed. So that will be the essence of a secure multi-party computation protocol, and that's where the secret sharing will be useful. Okay. So as I said earlier, due to lack of time, I won't be able to go through the multi-party computation protocol. With that, I would like to conclude my part of the tutorial. Are there any questions? Are there any questions here?
Yes, yes. No, what I'm saying is that I am taking a consent on them.
Okay.
Yeah. Okay. Thank you. No, no, that's it. Hello.
Hello.
Yes, sir.
So, are there any questions from the audience? Because I am done with my presentation.
We don't have as of now. I request everyone to post their questions, if any. So looks like we don't have any questions. So can we conclude the session, sir? If I have your permission.
Yeah. So, yeah.
So I'm concluding this session. Thank you so much, Dr. Ashish, for this wonderful tutorial. It was really insightful and very interactive, sir. And it was explained in a very simple language. Thank you so much for having. It was really
Thank you.
nice. Thank you so much.
Okay. Bye.